Hi everyone, in this video we're going to go through notes 1 through 3. In this video I might go pretty quickly, so make sure whatever notes you need you are fast forwarding to where you need to go. So we have matter. That's going to be the top of our flow chart here. And matter can be broken apart into two different categories, one of which is a pure substance and the other is going to be a mixture. Now, there are two types of pure substances. One is an element, and the other is a compound. And we're going to define those on page 6 here in just a second. And then a mixture could be broken down into a homogeneous mixture or a heterogeneous mixture. Okay. Now, matter is going to be our first definition that we're going to worry about. And matter is anything that has mass and takes up space. Okay, so if it has a density, you can get a mass measurement or a volume measurement for it. If you can get both of those, then it would be considered matter. There's three main states of matter. The first would be a gas. Gas particles are far apart from each other. Then we have liquids. Liquids, their particles are pretty close together. Not super, super close always, but typically pretty darn close together. And then we have solids, which generally are going to be the closest together. Okay, I'm going to flip to page 6. I want to do some definitions here because I think if I had to redo it, these definitions would make sense to come next. So with our mixtures, a mixture we need to know is a substance composed of two or more types of particles. Okay, and we have homogeneous mixtures and we have heterogeneous mixtures, and those prefixes are going to be pretty important. So the prefix hetero means different, and so a heterogeneous mixture is going to be a mixture in which the composition varies from one region to the next, or varies throughout. A great example that is used a lot, but I think it really hits the point, would be something like trail mix. Another one might be like a salad, okay? Not every piece of trail mix is the same. Not every piece of salad is going to be the same. Another is a homogeneous mixture, and this is going to be a mixture whose composition does not vary. And it's going to be a lot harder to come up with examples of a homogeneous mixture, but there's a couple that I can think of. One would be like Kool-Aid. Another might be something like Coca-Cola or Diet Coke, okay? I'm using Diet Coke just because that's what I prefer, but Coca-Cola definitely works, okay? So those are our types of mixtures. Okay, on the same level as mixture on our flow chart was a pure substance. Okay, a pure substance, very similar to the definition of a mixture. If a mixture is two or more types of particles, a pure substance is just going to be a substance composed of one type of particle at the molecular level. Okay, there's two of them. There's an element, and this is a chemical substance that cannot be broken down further by chemical means. And then we have a compound, which is a substance composed of multiple elements that are chemically combined. And we're going to come up with a few examples of those. An element, for example, is on the periodic table. So you could have carbon, you could have iron, which is Fe, you could have nitrogen, so on and so forth. A compound is going to be multiple atoms put together, so a great example is water, carbon dioxide, or glucose. And if we notice the way the formulas look, these are just one type of element, where in water we have H's and O's. In glucose we have C's, H's, and O's. Okay, so let's go back to page 2 now and get some more definitions. And I know definitions are not super fun, but there's something that we need to get through so we can make sense of other things. Atoms are going to be the smallest unit of a chemical symbol. And then all atoms of the same type have the same amount of protons. Molecules, on the other hand, are atoms, multiple atoms bonded together. And it's specifically nonmetals. Where formula units are going to be multiple atoms bonded together. And it's going to be specifically metals and nonmetals. So molecules and formula units, these guys are compounds. And then atoms would fall under the category of elements. And these particles at the particle level, whether you have solid, liquid, or gas, they are always in constant motion. And the higher the temperature, the higher the kinetic energy. There's a saying in chemistry called heat 'em up. Speed 'em up. Okay, meaning that the higher the temperature, the faster our particles tend to move. Kinetic energy, you may have seen this before, but this is going to be specifically the energy associated with motion. If you take physics, you will learn, or you may have even done this formula because it's not the world's craziest formula, but kinetic energy is equal to 1/2 mass times velocity squared. Velocity, on the other hand, is going to be speed, but specifically when you take physics, it'll be speed with direction. So for example, if I say 35 miles per hour, that's a speed, but if I say a car's going 35 miles per hour north, that would be velocity. Okay, here we have two positive charges. I have positive charge Q1 and positive charge Q2, and notice these F arrows. Those are called force arrows, and they're going opposite directions, and that's because like charges, they're going to repel. Where if we have positive and negative, they're actually going to attract. This is called Coulomb's law. And basically, just a rule that opposites, I almost wrote repel, but it's clearly opposites attract. Okay, so positive and positive, that's going to repel. Positive and negative, that's going to lead to an attraction. If we have negative and negative, they're the same, so that will also repel. Okay, let us classify states of matter. So solids, they're going to have a definite shape or a defined shape. Okay, not going to be a big deal to figure out the shape. Liquids, they're going to fit to their container. Okay, so for example, if I pour water in a water bottle, that liquid water is now taking the shape of their container. Gases are going to be similar to liquids, but I don't want to say that they fit to their container. I'm going to say that they fill to their container, or they fill their container completely. Okay, gases completely fill their container, whether you have a lot of gas or a little bit of gas, but they're going to completely fill. If you have more gas, you'll just have more pressure inside of your container. Okay, solids, they're going to have a defined volume. Liquids, they're also going to have a defined volume. We can just pour them into like a graduated cylinder and measure their volume. Gases, on the other hand, because they expand to fill their container, the volume of the gas is simply going to equal the volume of the container. The density, you may be aware of this. The density of solids tends to be high. Liquids also tend to be high, but I'm just going to put high to intermediate. There are plenty of examples of a liquid being more dense than a solid, but a great example would be solid water is less dense than liquid water, and that's why we see ice floating on water. And then gases, their density tends to be very low. That's why we can compress them, because there's so much space between the particles that bringing them closer together, there's all this space that we can bring them in. I'm going to jump to molecular picture, and then I'll come back to strength of interparticle forces. If we draw a picture of a solid, it might look something like this. Liquids might look very similar, and then gases way far apart. And if you notice, I'm not just randomly drawing these. I'm specifically following the law of conservation of mass, or of matter, that says if I have 6 particles, when I phase change and go to liquid, I'm still going to have 6 particles, okay? I'm not going to create or destroy any matter in a phase change. Because these particles are so close together for solids, solids have very strong intermolecular forces or interparticle forces. This makes sense. If I take a hammer and I use the hammer on a desk, I'm not going to break the desk most likely, because those desk particles hold themselves together really, really strong. When it comes to liquids, liquids also have strong intermolecular forces or interparticle forces. If I take my hand and I karate chop some water, I might be able to break those attractive forces and make my hand go through the water. But have you ever noticed that if you do that, once your hand leaves, the water is going to come back together, okay, because those attractive forces are very strong, okay? They're not as strong as solid because I can break them relatively easily, but those particles do come back together. And then gases, they're so far apart, there's very little attraction between them. And so gases have very weak, and I might even say almost none. It's not none, but it's pretty darn close to zero attractive forces. Okay. Now, on your periodic table, you should see a stair step here, and this stair step is kind of important because it helps us see that this side of the periodic table, this is metals, where this side is nonmetals. Hydrogen is an exception. Hydrogen is a gas and it's a nonmetal. Okay, so let's talk about the differences between metals and nonmetals. You probably know this just from your experience in the kitchen, but metals are going to conduct electricity and they're going to conduct heat, and they do both well. On a chemical standpoint, metals, they get oxidized. And that means that they lose electrons. Nonmetals, on the other hand, are just opposites of metals, so that doesn't mean they don't conduct, but they're just poor conductors. And the opposite of oxidize or oxidation is called reduction, so they get reduced, and that means that they gain electrons. Metals are all solid at room temperature. Except mercury. And mercury has a chemical symbol Hg. It's right here on your periodic table. Nonmetals, most of them are gas. We do have one liquid. Bromine is a liquid. And then carbon, silicon, phosphorus, and iodine are all solids at room temperature. Okay, these all elements could be solid, liquid, or gas. You just have to get it to the appropriate temperature. Okay. Now, there are 7 diatomic elements. The prefix di means 2 and atomic means atom. So these are elements that exist in pairs in their elemental state. And we have 7 of them. We have nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. That's 6, and then hydrogen. So notice we have 7 of them. Just so happens that they form a 7 on your periodic table, so that might help you remember. But don't forget your hydrogen. Now, we have a little acronym to help us out, and we call it Brinkelhoff. So bromine, iodine, nitrogen, Brinkel, chlorine, and then Hoff, H-O-F. And so what I mean by a diatomic element is if I have the element bromine, it's never just Br. If it's all by itself and it's just the element, it would really be Br2, or I2, or N2, or Cl2, or H2, O2, or F2. Okay, we've done these definitions. Now let's come back and fill in this table. Go ahead and think if you can name some elements. So I'm just going to name 4 or 5. So I could do carbon, zinc, potassium, or calcium. And notice that it's either one letter or two. The first one is always going to be capitalized. The second one, if it exists, is always going to be lowercase. And we have no more than 2 letters. A compound, an element can be an atom. A compound could never exist and just be an atom. So this does not exist. Okay. A molecule is going to be between nonmetals. And an example of something that is an element and a molecule, we need more than one atom. If we go back to our compound, it's multiple elements. So an example would be something like our Brinkelhoff elements. Or nitrogen, hydrogen. We have other types of elements like sulfur commonly exists as S8, and then ozone in the atmosphere is another version of oxygen as O3. And then a compound is going to be something with different elements. So we have something like H2O, CO2, C6, H12O6. So different elements are going to be in a compound. A formula unit is going to be between metals and nonmetals. Okay, and this does not exist. We can't have something that's an element, one type of atom, and then also be metal and nonmetal. That just doesn't exist. But we have plenty of compounds that are formula units. A common example would be sodium chloride. We could have calcium oxide. There's a lot of different things that we could have. Okay, you can pause the video and read about elements and compounds and then mixtures. We've gone over these, so it should be review. What I want you to do is pause the video and do these practice problems. Classify each of the following as elements, compounds, or mixtures. And then if it doesn't fall under any of those categories, write an X. And for your compounds, put FU if it's a formula unit, or write molecule if it's a molecule. Air is actually not an element. Air is a mixture of like nitrogen, krypton, argon. Okay, so some of those maybe are a little tricky, like electricity or energy. You might have had to think about that, but those are going to be none of the possibilities that we had. Okay, Now, in these practice problems, what I want you to do is we want to classify it as a pure element. A pure element has one particle type. And, for example, it might just be a circle, okay? A mixture of two elements might be two circles of different types. A pure compound would be multiple circles together, so touching, but just one type of particle. So maybe something like this. A mixture of two compounds, we're going to have two different combinations. A mixture of compound and element, we're going to have a compound and then an element. So a compound's going to be multiple circles put together, and an element's going to be one type of circle here. Okay, so go ahead, pause the video and try some of these out. I'll do the first four and then just give you the answers on the next ones. And if they have different colors, that means that it's going to be not the same compound or element. And if they have different sizes, they're not going to be the same compound or element. So this first one is just a pure compound. We just have one type of particle that's white, black, white. White, black, white, white, black, white, and they're touching, so three different particles. Here we just have a pure element. Here we're going to have a mixture of compound and an element. Here we have an element. Here we have a compound. And then this is going to be a mixture of two elements, okay, because we have two different types, a white circle and a black circle, but just one circle. This next one is going to be a mixture of compounds. The reason why is they're not the same. We have white, black, white. Here we have black, white, black. This is going to be a mixture of compounds. You could make an argument that it's also a mix of elements because this could be like oxygen, O2, 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 and then O3, so it's just one type of atom present. This is going to be a mixture of compounds, or you could say compound and then an element there with the two white circles. This is going to be mix of compound and element. This is going to be a mix of compounds. This is going to be either an element or compound, but either way pure. Same difference here. This is a pure compound. I know that this goes white then black, and then this one goes black then white, but think about it, it could be rotated different ways. This is a mix of elements. This one is just a pure element. This is a mix of elements. They're different sizes, so we can assume that they're different elements. This is going to be a mix of elements as well. And then this, oh, I put electron up. And then this is going to be a mix of elements. Okay. Now, let's finish notes 3. Notes 3 shouldn't take very long, and then we'll be done with this video. So, a physical property is something that can be measured or done. Well, I guess a physical change. A physical property is something that can be measured without changing the composition, okay? So, for example, we can heat something, we can cool something, we can rip something in half. Those are all physical properties. But whether I heat water, cool water, whatever, it's still water. So, the key idea here with the physical changes, we have no change in the chemical composition. Okay, it's still the same formula. Now, a chemical property is something that's going to talk about dealing with the chemical reaction. And we're going to get a chemically different substance. We're going to get a new formula if we undergo a chemical reaction or a chemical change. Okay, a chemical change is going to be something like burning, tarnishing, oxidizing. These are verbs that we tend to see when we're undergoing a chemical change. Now, evidence might be like a color change. Production of gas. Production of solid. Smell change. There's a lot of things here, but just because we produce a gas, for example, that does not mean that it's for sure a chemical reaction or a chemical change, because when I boil water, that produces a gas, but it's still water vapor. It didn't change the formula. So we've got to be careful. Physical properties, we have some malleability. This is the ability to be shaped into something. I put a horseshoe there because metals are typically good at that. Ductility, the ability to be pulled into a wire without breaking. Copper is really great at that. Solubility, when you dissolve something, and I want you to write this down because a lot of students get this wrong. Dissolving something in water is a physical property. Okay, this is because if I evaporate the water, you get back the same solid. Okay, melting point and boiling point, freezing point, a lot of different things. Those are also physical properties. Okay, an intensive property is something that does not depend on the amount of matter present. So we could talk about density. Whether you have a lot of water or a little bit of water, its density is 1 gram per milliliter. Boiling point. Whether you have a lot of water or a little bit of water, it still boils at 100 degrees Celsius. Conductivity. Okay, whether I have a lot of metal or a little bit, it should still conduct electricity. Extensive properties are things that you can measure and that change. Okay, this would be something like mass. We have different masses for different compounds. Volume. Okay, whether you have a big sample or a small sample, the volume might change. Okay, so go ahead and fill out 1 through 10 and then 11 through 19 and then 20 through 26. Pause the video and then I'm going to go through and answer them, and you can check your work. Again, it doesn't help you to just write down the answers and then never go back and look at it. Yes, you get something done, but you're not learning anything or really putting what you learned to the test. Okay, so go ahead, pause this, and answer these questions. Dissolving is physical. Melting is physical. Burning is chemical. Okay, we get a new substance. We get ash or something. Baking, a lot of cooking is actually a chemical reaction. Dissolving, that is going to be physical. Iron rusting, rusting is oxidation, and that's going to be chemical. Writing on a chalk, that's physical. Silver tarnishing, that's going to be chemical. And burning, that's going to be chemical. Mass is extensive. We can measure it. Volume, we can measure it. Length, we can measure. And so the rest are going to be intensive. They don't change.